Hello, my name is Vlad. I am a C and C++ developer with roughly 8 years of experience. Right now I work at a game dev company called Ubisoft, which some of you probably heard about, with mostly low-level networking and some bits of system programming. And in Ubisoft, while doing a complete rewrite of our networking stack in one of game engines, I managed to design, I hope, a cool algorithm for doing so-called task scheduling. And today, I share this algorithm in the form of this talk and an open source C++ implementation of it. Although, if you don't like C++, it doesn't have to be it. Today we focus just on the algorithms, and they can be implemented in some other language too, like in Rust, I'm sure it can be done, in Java, in C# maybe. So there will be a lot of content, so we will be going relatively quick, and I ask you to concentrate. Talk will follow the plan. Firstly, what is task scheduling exactly, because many things can be understood as it. Then I explain how it's normally done, what are typical problems with it, at least known to me, and how worked an old task scheduler in my game engine, and how works the new one. And then I will briefly show you the benchmarks, how it's verified, and what are the future plans for it. So what is task scheduling exactly? Today, in this talk, I mean as task scheduling any kind of execution of code, such as callbacks, functions, or something similar, and we just call it task, a generic term. And so to give you a few examples, tasks can be callbacks in a thread pool, or tasks can be watchers in an event loop, like in libf in C. We can have watchers as timers or wrapping sockets, and they also have callbacks. Or we can also call tasks coroutines in some coroutine engine like C++ coroutines, or fibers in Tarantul database. So here is a very, very simple trivial scheduler implemented in C++ like pseudocode for simplicity, which demonstrates this example. So it's just a single thread. It has a mutex locked queue for callbacks, and what it does is just executes those callbacks one by one. This is a very simple scheduler. Now let's see if such a basic scheduler can solve a real task, which I had at Ubisoft. Here, tasks execute requests coming to a server, and they handle save game blobs. And there might be tens of thousands of those requests per second, and they are also CPU intensive. So every task might take milliseconds of pure CPU time. And also, they consist of multiple steps, like I have to, in each task, lock user profile in some database. Then I have to download the save game blob from another database. Then I have to do some pre-processing of this blob, some stuff with it, some manipulations. Then I have to upload it back and unlock the user profile. As you can guess, most of the time, the task is not doing anything at all. It just sleeps, waiting for network input from the databases. So literally, more than 90% of times, there is nothing happening in this task. The trivial scheduler, which we just saw with single thread, it will not work here. It simply will not scale. Firstly, single thread is not enough to handle so many requests, being so CPU intensive. It will just choke on CPU. Secondly, we can't postpone blocked tasks and do other tasks while the first ones are waiting for some events like network input. So this means we need coroutines so that tasks could yield, so they could give up their time to some other tasks in the same thread. The game engine I'm working with had a good enough scheduler which could do the job for some years good enough. This was just a thread pool where each thread had a list of own tasks, and when new tasks were appearing, they were distributed to those threads in a round-robin manner one by one, and they were pinned to those threads forever. They could not migrate between threads. And then what each worker thread does is updates all its tasks with some fixed hard-coded period, like once per 100 milliseconds or once per second. Each task, after being updated, it can return false eventually, and it consider it done, and it is deleted. So this is some polling, basically. And we will call this scheduler updater because there isn't much scheduling, really. It just updates those tasks without looking at their state or anything, so we call it updater. This updater thing had some typical problems, like schedulers of this type sometimes do. Firstly, it was unfair, meaning that tasks were pinned to threads. They could not migrate. This leads to a problem that your CPU usage will be unbalanced, because some worker threads will get heavy tasks, and a lot of them will stay in the queues, and other threads will get light tasks and will be in idling most of the time. This will happen even if you do perfect round robin and all your tasks are the same, because actually tasks are never the same. Like in my case, all the tasks do the same several steps, but save game blobs, they can vary in size from kilobytes to megabytes. Their processing, their downloading obviously takes not the same time. So some threads will be unfairly loaded, and they will perform worse, at least in terms of latency, because they will have bigger queues, tasks will wait longer in them. And that is not the only problem. The other problem is polling, which in this case means each task is updated unconditionally with some fixed period regardless of task state. So every task is updated even if it doesn't have work to do yet. So it's still waiting for network input. What it means is that if you select too big polling interval, then you will have too high latency, more than you could have. For instance, imagine like we have a task with just 3 steps, each taking 5 milliseconds, and in between it waits for some network input. And we will update it once per 100 milliseconds. Then your task will always at least take 215 milliseconds. The thing is, you don't always need so much time. Most of the time, like almost always, the network response will arrive earlier than 100 milliseconds expire, and you have events to process, but you are not doing it because it's not yet time to update the task. So we have higher latency than we could have. If you try to fight it, try to set lower polling interval, then you will burn CPU without need, because you will have spurious wake-ups, so unnecessary wake-ups. You will sometimes wake up tasks before they have stuff to do. It doesn't sound too bad, like how expensive can it be, really? And imagine like spurious update of a task would cost us just 10 microseconds to check a deadline or check an atomic flag, lock and lock a mutex, and that's it. It's not much, but if you have 10,000 tasks per second doing those unnecessary wake-ups, you just burned 10% of one CPU core, which already sounds worse. And this problem aggravates if you have more threads than CPU cores, because then you didn't just burn the CPU time, you stole it from other threads, which could spend it on something useful. This problem was actually real. And during load tests, some servers were spending more CPU time on spurious wake-ups than on doing actual work. So they were just burning. So much for the green data clusters. What we need on the summary from a really performance scheduler. Firstly, it should be fair. We are not allowed to pin tasks to threads. It doesn't scale. Secondly, we need coroutines, so that tasks could give up their time, so they could yield and let the worker thread do some other work, other tasks. And also we have zero tolerance against polling, no polling at all. Everything should be event-based. And these goals are achieved in a new scheduler, which I, due to lack of fantasy, just called the task scheduler. But although the name is pretty self-explanatory what it does, the plan is that we will go, firstly, we'll look at the big picture, at the entire scheduler, and then we will look at individual parts of the scheduler, and you will already know what they do. Imagine like we have a process, this server running, it's a process, it has multiple threads, and they produce tasks. And we have a global object of type task scheduler in the process, like it can be C++ task scheduler, Java task scheduler, whatever language you implemented it in. It is a global object in the process, and those threads, they produce tasks. So they receive some requests from clients and wrap them into tasks and post into the task scheduler in form of some callbacks of some sort. In the scheduler, they will gather in a so-called front queue. Then the scheduler will periodically pick up, take all the tasks from the front queue and inspect them one by one. It will see that some tasks are ready to be executed right now, the red ones on the slide. They want to be executed ASAP. And some other tasks, they do not want to be executed right now, they just yielded. We have coroutines, so there will be tasks which don't want to be executed now. They are waiting for something, for a deadline or for an explicit wake up for some event. They are moved into the wait queue, where they will wait for their events. Also from the wait queue, we extract some older tasks which were already sleeping there for some time, and now their deadline is up, or they were woken up explicitly. Either way, we extract them from the queue, and all those red tasks go to the ready queue. And from here, they are extracted by the worker threads, which take them from the ready queue one by one and execute. And this is basically the entire pipeline. It's not too complicated, although some of you could already have a question, who does this part? We have external threads posting tasks. We have worker threads doing tasks, but who does the scheduling itself, management of the queues? The thing is, there is no dedicated thread doing just the scheduling. Instead, the worker threads compete for doing the scheduling, depending on who of them is idle. So imagine like this big rectangle with queues, it's a room with a single key to it. And the worker threads, sometimes, depending on who of them is idle, again, will try to pick out the key. Whoever does it first enters the room, does the scheduling, this queue management stuff, leaves the room and starts doing tasks. So all the threads are the same. There is no threads having roles of some sort, like a naive implementation could do. And it's a bit like dining philosopher's problem, except that we have just one fork here. And this big rectangle in this case is just a plate of spaghetti, but not in code. Code is clean. To improve understanding, there is a short visual example I prepared. Imagine like we have 5 tasks. They are posted into the front queue, and one of the worker threads has the scheduling key right now. It will extract the tasks from the queue. We'll see that a couple of them yielded. They go to the wait queue, waiting for something, and the others are moved into the ready queue. From here, they are picked up by the worker threads. Nobody is doing the scheduling right now. All the threads are doing some actual work. A couple of tasks are done, and suddenly those waiting tasks are woken up, or their deadline is up. They want to be executed now. So one of the worker threads will eventually pick up the scheduling key, will notice this, will move the tasks into the ready queue, and in parallel, some other thread finished on older tasks. Now those 2 tasks are picked up by a couple of random threads. They are done, and some other thread will pick up the scheduling key, and the process repeats all the time when new tasks arrive. This is it. What we need to implement all this cool stuff, the language and the libraries which we will be using need to provide us with the following stuff at least. We need mutexes, containers like arrays, lists, condition variables, and not important for the algorithm, but for the implementation, for the performance, it's extremely important. We will also need log-free atomic operations. Just in case not all of you know what they are, here is a short pseudocode explaining what these log-free atomics are. We will need 3 of them. Firstly is atomic load, which is basically reading a variable, but with respect to so-called memory models, which you can Google afterwards. It's too complicated topic to dive in right now. We will also need atomic compare exchange, which is conditional assignment. So we set a new value to some variable if it was equal to something else which we wanted to check. And we will also need atomic exchange. So it sets a new value and returns the old value. The cool stuff about those log-free atomics is that they are not only atomic, but they are lock-free. There is no mutexes. On the contrary, mutexes use this stuff inside. And how they are implemented, they are special instructions right on the CPU. So doing those operations doesn't even involve the kernel. It's quite cheap if you use it efficiently. And those free operations are basis for some very cool and extremely performant algorithms, as we will see. Not just here, there are a lot of those algorithms based on those lock-free atomic operations, and they are also called lock-free algorithms. And we will follow the task pipeline, looking at the scheduler parts, and we will start from the front queue, just like the tasks. We know that this queue has multiple producers and it has a single consumer. So it means this queue is multi-producer, single consumer. This is a common notation for naming queues. We say multi or single producer, multi or single consumer, and we get 4 combinations of queue types. This is multi-producer, single consumer. We also know about this queue that it will experience high contention because I want my scheduler to be functional when I have tens of threads and millions of tasks per second. This means extreme contention on the front queue. This in turn means I should avoid mutexes because mutexes most likely will choke here. What you would do in a normal queue, not thread safe or anything, you would have to remember 2 positions, head and tail, and maintain those positions. If you try to turn this algorithm into a lock-free thread safe implementation, it would be a nightmare because operating on the more variables you have to update in a lock-free way, the more complicated the algorithm gets. And queue, like with 2 variables, it's extremely hard to implement in a lock-free way. We should try to avoid this if possible, and the idea is let's make it a stack instead of queue. So we will maintain just 1 position, the top item, and that's it. We don't need 2 variables here, and then the algorithm becomes quite simple. Pushing is, well, we try to link new item with the old top, set it, atomic compare exchange will fail if some other threads does it faster than we are in this push, and we then retry it. It's pretty simple. The more complicated part, although it looks shorter, is popping the items. The thing is that how pop is implemented, we just replace top item with null, effectively taking all the items at once. We cannot pop them one by one. And also we have to reverse the list before we return it, because when we were pushing items in FIFO order, pushing them on the stack, they are returned in LIFO order, and we want to maintain the order, so we have to reverse it again. These are 2 downsides that we can't pop one by one, and we have to reverse the result before returning it. On the other hand, what we get, it is completely lock-free, thread safe, and it's weight-free. Who will win those drawbacks for the being lock-free and weight-free, we will see in the end in the benchmarks section. Next part of the task journey is wait queue. As we know, it stores yielded tasks. So they are waiting for something, like in 99% of cases, they are waiting for a deadline. Since we're using tasks for requests usually have a timeout, meaning that they have a deadline. So what we need is to be able to quickly pop all tasks with expired deadline. Simply because we have to do everything here quickly, there is a lot of tasks. And we also know that this queue is always accessed by 1 thread at a time. The current scheduler worker who owns the scheduling key, so there is no concurrency on this queue. And that gives us quite a lot of freedom about what data structures we can use. And that basically means we can use binary heap. It's ideal for such job when you have to quickly pop something sorted by thing like deadline. What happens is that we sort the tasks by deadlines here, basically. So the task with the closest deadline will be on top, and we will be able, for constant time, tell immediately if any task has expired by just looking at the top. And in case not all of you know what binary heap is, there is a brief explanation. It's a perfectly balanced binary tree where each node value is less than values of its child nodes. We call this minimal heap. If we reverse the order, it will be called maximal heap. And this heap, it has quite good complexity. So for logarithmical time, we can pop any items, even from the middle. We can push new items also for logarithmical time, which is very nice, very fast. From the wait queue, the tasks migrate to the ready queue, which, as we know, is populated by one thread, current scheduler worker, and it is consumed by multiple threads, worker threads. So it means this is a multi-consumer single producer queue. We also know that it will as well experience high contention because task scheduler should be perfectly functional with like 10 worker threads, why not? And with millions of tasks per second, we will have high contention. We have to deal with it somehow, although unfortunately I don't know a nice simple algorithm for doing unbounded and lock-free queue of this type. For the reason why, you can Google ABA problem after the talk. It's also quite complicated. We will not have time to dive into this. But just know that it is much more complicated than multi-producer single consumer version. Although I know a couple of other queues, unbounded log-based and bounded log-free. I want my final queue to be exactly unbounded, meaning not limited in size. So I don't want any limits inside the scheduler. You can add them on top, but I don't want them to be inside the scheduler. I don't want it to be limited by anything like queue size. So let's see what we can do with those two queues. The bounded log-free version, bounded log-free queue is simple. It's just a cyclic array, except that the read and write index, we make atomic variables. So in pushing, the only thing changes compared to normal cyclic buffer is that you increment the write index atomically. Atomic increment, and that's it. And popping, it's just a little bit more complicated. We have to retry it sometimes because there will be multiple consumers. They will compete for the same element sometimes. So atomic compare exchange will eventually fail and we will have to retry, but it's still quite simple. And the unbounded locked queue is just trivial, so it's a mutex and it's a list, and we take mutex on every operation. Then it becomes log-based, but it's unbounded. So what we can do with the ready queue? What I had was the craziest idea. The thing is, our enemy is not the mutex itself. It's the contention on the mutex. So we could try to reduce the contention instead of deleting the mutex. We could keep it, but somehow maybe not lock it so often. Let's combine those two approaches together. Let's take the bounded log-free queue and make unbounded log-based queue of those log-free sub-queues. So it will be like a steady queue, but the blocks are log-free. And the big queue of those blocks is log-based. Then the producer, how producer works, it will push new items to the latest block in a log-free way. When the block becomes full, it takes mutex, appends a new block, fills it in a log-free way, and so on. And the consumers, they do their other thing, vice versa, so they consume the first block in a log-free way. When it becomes empty, they take mutex, switch to the next block, consume it in a log-free way, and so on. To see the benefit, imagine like sub-queue size, this block size, it's not 4 like on the slide, but it's 10,000. What happens then is we will take mutex lock not on every operation, but once per 10,000 operations. Mutex is still here, but it's locked so rarely that its cost is neglectable. You will not see this mutex lock in any flame graphs anymore. The only problem with this is that the consumers will need an explicit state. Because if consumer doesn't know which is the first block in this queue of blocks, it will have to locate it. The queue of blocks, it's protected by a mutex, so if consumers don't have a state, if they don't reference the first block having items, then on every pop they would have to find it, keeping the mutex, and that would mean mutex lock on every pop. This is exactly what we wanted to avoid. So consumers need to register themselves, and then they can do the popping. This is not a problem for a task scheduler itself because it has fixed set of worker threads which you specify at creation. They can register themselves as consumers at start and live just fine with it. So it's just a problem for generic usage of this type of queue, but for task scheduler, it is just fine. Let's examine a visual example again. Imagine like we have this queue, it's empty, just single block, one producer, two consumers. Producer adds 3 items in a lock-free way. Everything lock-free, so it is lock-free so far. One consumer consumes 1 item, lock-free. Now producer adds another item block-free. It sees that the block became full, so we need to append a new block. We take mutex, switch to the next, append the new block, switch to the next block, release the mutex, and add 3 more items in a lock-free way. How consumers will work, they will finish consumption of the first block. Consumer A will see that the block is empty, so it takes mutex, switches to next block, releases the mutex, and continues consumption in a lock-free way. So we take mutex only when we switch from block to block. And the other consumer, when we will try to consume something from it, it will see immediately that its current block is empty, because those blocks, they are, as you remember, lock-free bounded queues. There are read and write index. If we see that the read index of this block equals its size, it means it's empty, so we don't even need to full scan it. Anyway, consumer B will then lock mutex, switch to next block, release the mutex, and continue the consumption. And the old blocks, the completely consumed ones, can be discarded. You can free them, you can reuse them, like have a pool of those blocks and append them to beginning again. If you want to, like, it's not cheap to allocate blocks having 10,000 items in them, so you might want to pull them, to have a pool of them. About the benchmarks, we will see in the end. Again, as I said, with everything combined. And our progress so far is that we saw task scheduler parts, those queues, and now we can have a glimpse at the coroutines. Unfortunately, we don't have enough time to dive deep into the implementation, but I can show you some usage examples, show the features they have, and for the implementation, you can look at the source code and ask me questions after the talk. To see why do we need coroutines again and what features we need from the coroutines. Let's inspect a simplified version of this save games example. This time we have just 2 steps. Start download of a save game blob and then handle the result. This is in just 2 steps. What we know is that while the task is waiting for response from the network, it shouldn't block other tasks, so it should be able to yield. It should be able to step away. But we also know that this task, it can't sleep infinitely. There should be some sort of timeout. Requests can't be executing infinitely. So we need some deadline after which the task would be woken up and will cancel the request. Also, if the response arrives in time before the deadline, we have to wake up the task before the deadline. There should be some sort of explicit wake up for the task which is right now sleeping in the wait queue, so it's not executing. How exactly do we wake it up from there? So we need an explicit wake up. We need yield, deadlines, and wake ups, 3 main features of those coroutines. Let's see an example. It's almost exactly like it looks in real code. There will be simplified version of C++, but it's very similar how it looks in reality. We have a global task scheduler in the process and some HTTP client. And imagine like a request from the client arrives, so we wrap it into a task and give it a callback called download. And we post it into the scheduler, so it will go into this front queue. The scheduler will execute our callback in one of the worker threads, this download callback. So what we do here is firstly set what will be the next step. The next step will be handling the result. Then we do the asynchronous HTTP request. Assume that our HTTP client is able to do this. So we start an asynchronous HTTP request and give it a future callback to execute when the request is done. which will call wake up on our task. So this will be explicit wake up when the request is done. And then we start waiting. So we post ourselves back into the scheduler with 5 seconds deadline. Either the task will wake up in 5 seconds, or it will be woken up explicitly when the request is complete. The task goes into the scheduler, sleeps in the wait queue for some time, and eventually our callback handle result is executed. We have to check what happened. It could be 2 reasons. It could be that the task is expired, so 5 seconds passed and we were woken up by the deadline. And we just literally check if it's expired. If it is so, then we cancel the request and we start waiting for the cancellation to be complete, to properly free all the resources, and so go back into the scheduler, but now we wait for the cancellation. Otherwise, if it's not expired, that means the request is finally complete with some result. It could be success, it could be an HTTP error code, or it could be our own cancellation done on a previous wake up a few lines above. Either way, we just handle it and delete the task. This is literally it. This is almost exactly how it looks in the source code. There is no spurious wake-ups at all, no sleeps, and the request has clear state machine with every state expressed as a callback. And what is better, these entire routine stuff, all those wake-ups, post, deadlines, this is all completely log-free. There is no single mutex used to implement this all. So this is to get you further interested into looking at the source code and asking questions afterwards. This is quite complicated stuff, as you can imagine, especially the implementation. How do we verify such stuff? Of course, there are unit tests, like literally hundreds and thousands of lines of unit tests, but with multi-threaded algorithms, the thing is, even if you have 100% code coverage, it doesn't tell you anything. Like, it's better than nothing, like not having 100% coverage, but it's still there might be bugs, which can stay hidden for literally years, and you will not find them except when this thing explodes in production. There should be a way to at least verify the algorithm, maybe. We can't verify the source code, but we can improve our confidence about the algorithm itself. And the solution is TLA+. TLA+ stands for temporal logic of actions, and it is a combination of mathematics and temporal logic. And it's also a language and runtime of this language. This language allows you to verify literally any algorithms or systems. Like you can verify an algorithm of a queue, like I did, or how your microservices interact. Or you can verify how you go to a grocery store. If you can algorithmize it, then you can verify it. TLA+ is suitable for anything like this. So in this TLA+ language, you write a specification and run the verification, and it will split your system, your algorithm, into a set of all the possible states in which this algorithm can be, and verify your own invariance in every reachable state of your system. So firstly, you define the algorithm, then you define what means validness for your algorithm, the invariance, and TLA+ will verify all them. Let's see an example, like assume you have implemented a queue in any language, and we want to verify the algorithm of this queue. Firstly, you have to define what objects exist in your system, what agents you have there. In my queue, I have just pipe for items, so some sort of storage, and a couple of counters and limits. Then you have to define actions. In TLA+, every action is a set of mathematical conditions combined with some mathematical operators, like you have operators and or operator, or list or set operator, or complex operators like all items in a set comply with the condition operator, and many more other operators which you can use in your actions. And the first action is always initialization, where you give initial values to your variables. Here I say that storage pipe is an empty list and my counters of sent and received items are 0. Then I start defining some actual actions doing stuff, like send or push or insert or whatever. And there are ways how to do it. I'm not aware of any standard ways how to do it properly, so I invented my own. Firstly, I split my actions into two groups. In first group of conditions, I define when the action is possible. So here I say send is possible when queue is not full and when I still have items to send, so not everything pushed yet. In the second group, I tell what changes should be done when the first group is true, so when the condition is true. Here I say if the first part is true, then I add a new item to the pipe storage. As items, I use numbers, and I increment the number of sent items, of pushed items. The problem is, as you could see, probably there is no really distinction between those two groups. It's imaginary. And the only distinction is this small single quote sign. It means next value of the variable. The problem is, since TLA plus is basically math, in math there is no assignment. There is no action like assign new value to some variable. There is only, the closest thing we have is equal operator in math, but there is no assignment. But you can emulate it saying like next value of your variable equals old value and something done with it. So here I say literally last sent next equals last sent old plus one, which effectively results into assignment in programming languages, but here you have to simulate it like this. In TLA plus there is no separation into groups, it's just several mathematical conditions, but I do separate it for making the specification easier to read. I do the same for the receive action. It's possible when I have items to receive and the changes are do receive. And then you have to define what means validness for your system, so the invariance, which will be validated in every reachable state. Here I say that my queue is valid when all the items in the queue are ordered like I pushed them, that the queue never overflows, and then the items are received in the same order as sent. And then with some technical steps, simple ones, I run the validation, and it will give me a result, like n states are found, like hundreds, thousands of millions of states are found, and all are valid, or it will say that I found an invalid state. And here is how you get into the state from the initial one following this sequence of actions. And then you can turn those failure traces into unit tests in your actual code. So this actually works, and they caught a bug in task scheduler thanks to this thing. Here, by the links, you can find the specifications for task scheduler on the whole and for the multi-consumer queue, which was not trivial enough, so as I would try to validate it as well. Two specifications, they are quite big, but most of the lines are comments explaining the algorithm. So the specifications, the code part of them is not too complicated. You can read it like easily. And also there are instructions how to install TLA Plus in the source code repository, how to run validation on those models, how to install TLA Plus into the command line. It's not trivial, surprisingly. And there are also a great course of lectures from the author of TLA Plus, Leslie Lampert. The lectures are quite fun. If you are not planning to use TLA Plus, they are still worth watching. Very entertaining. All of this can be found in the source code repository. And now about the benchmarks. How I did them, the benchmarks are comparative. So I'm not just running the benchmarks against themselves in vacuum against some random stuff. I compare the improved versions of those my algorithms against trivial versions, naive versions using mutexes to see if stuff actually improved. Like all the same benchmarks run on my algorithms and on trivial implementations. For example, the smart queues I benchmark against their mutex locked versions, or the task scheduler I benchmark against thread pool, without coroutines, single queue, single mutex, and nothing else. I run this on 5 different configurations of software and hardware with tens of scenarios, and all the reports about the performance are available on GitHub in human readable markdown format. And you can also run them on your system with just a single line of Python script. It will generate the report for your case, and you can read it and see what's up. So there are quite a lot of results. I can show just a few of them on the slides. I will use Debian Linux with 8 cores running in Google Cloud, and I will show just some average results. No shocking, like 100 times faster, although there are extreme cases when algorithms are almost the same, or when it's extremely faster, but I will show just some average results which you can actually get in real production. So we start from the front queue again. The benchmark uses 5 producer threads and 1 consumer thread doing busy loop pushes and pops all the time to get the worst case contention. It's just for 1.5 times faster, and this is all considering the 2 drawbacks which you can remember. So we store items as stack in the front queue, we have to reverse them, we can't pop them one by one, and still it is 1.5 times faster. If we make it 10 producer threads, so we have more threads than CPU cores, worst case for mutex contention, it becomes 2.6 times faster. The ready queue, another benchmark, 5 consumer threads, 1 producer thread, again busy loop, pushes and pops, it becomes 2.6 times faster already, and you can see that the mutex, the lock contention is multiple orders lower than in a trivial implementation. This is thanks to us taking mutex lock not on every operation, but once per multiple thousand operations, and this is the result. Mutex is still here, but it almost doesn't affect the results at all. When we make it 10 consumer threads, it becomes already 4.5 times faster. The naive queue degrades quite quick in this case. And now everything combined, the task scheduler on the whole. In this benchmark, tasks are empty, so they are just empty C++ functions, not doing anything. Worst case for contention again. And now we start from single worker thread, which will do both the scheduling and tasks. It becomes right away 2.2 times faster. Then a trivial thread pool without coroutine support, it becomes already 2.2 times faster. And 0 lock contention. So lock wasn't contended even once between the worker and producer. When we make it 5 worker threads, it becomes 3 times faster. So it scales better than naive implementation. When we make it 10 worker threads, it becomes 7.5 times faster. And these are not the best results. It can be even better. I'm just not showing extreme cases here, but I saw like 15 times speed up as well. It's just not something you will most likely get in production if you start using this, but those benchmarks are also available. And now about the real usage, not some random benchmarks in the vacuum, how it affects the actual code. Applied to this save games case from the beginning. We ported one of the microservices from updater scheduler to task scheduler, and we immediately, without any further optimizations, got 10 times speed up. We went from hundreds RPS to bigger than 10,000 RPS, and latency dropped 5 times, like right out of the box before we started doing some other optimizations. And the algorithm is extendable. So as you remember, there is this big rectangle where only 1 thread at a time can work. It means this is thread safe space. We can replace the binary heap with waiting task with something more complicated. For instance, we can put libf inside, or epoll or IO completion ports on Windows inside, and we get multi-threaded event loop, like multi-threaded libf. We can store sockets in tasks, and we get sockets with deadlines, with yields, and this is in fact what we do have in Ubisoft. It's a fork of task scheduler where we just replaced wait queue with epoll on Linux and IO completion ports on Windows. And we get more than million messages per second with just several threads on sockets with this thing. It's not too complicated to extend scheduler, it's just maybe next time about this multi-threaded event loop. What are the future plans for it? Firstly, we could try to run it on ARM. Maybe it already runs, but I just haven't tried. So maybe it works, maybe not, I have no idea. This is why it's open source. You can try it, send a pull request if something not working. Also, it's currently implemented only in C++, and it's not even STL, although some people might consider it good, like me. I don't like STL, but it could use a port to STL as well, or to some other language. And also there could be optimizations done like the front queue. Maybe there is a way not to store it as a stack, not to reverse the list of items before returning it. I just haven't found a simple way to do it, which would be worth trying. And this is the end. Thanks for your attention. And here are the links to the source code and to this talk. It will be available, the animated versions with all the slides and my notes online by this link and my other talks. And also there are bonus sections which some of you might ask us questions and we will quickly go through them, or you can click on them yourself after the talk if you're interested. This is it.
Okay, so time for questions. So show of hands, and we'll give you a mic.
Optimization suggestion. So for the front queue, you can use some of Dmitry Vyukov MPSC queue, they're really fast, much faster than Triber Stack, which is the thing you're using. The other thing is for the wait queue, well, you answered this with IOCP, KQ, EPOL, that would be much more in line with something that uses timer or for networking. And you said that we cannot have
multi-consumer single producer. Right?
Yes, you can actually. You can use one of the Chase-Lev DQ. There's a paper for 2013 with formally verified primitives, including ARM, and those will work for your use case.
I know that there exist implementations of such queues. I just couldn't find the simple enough one. The thing is, in Ubisoft, internally they, above all, sometimes in harm to performance, can value code simplicity. So it's not an option to use something extremely complicated, like hazard pointers or stuff like this. Or, for example, I saw implementations of such queues which are not wait-free, so they can be lock-free, thread safe, but not wait-free. That also wasn't an option because that's basically a spin lock.
Those 100 lines, is it simple enough? Because you can have something unbounded in 100 lines using one of those formally verified queue as a basis. I can show you later if you want.
Yeah, we can talk about it. Probably I'm not aware of this one.
So did you start it with the C++ code or with TLA plus?
What?
Did you start it with the code or with TLA plus?
Solve what?
With your whole architecture, your new scheduler.
Firstly I wrote code, of course.
Okay.
And then I verified it.
Okay. So second question, did you have any in-house experience with TLA plus or did you learn everything from scratch?
I wrote it from scratch, so I decided I want to verify this because I'm afraid for it in production, what will happen if something goes wrong. So I was aware of TLA Plus existence before. At some other conference I heard a great talk about it and I wanted to try. So I started listening to Leslie Lampert's lectures. I watched them all, started trying some simple stuff like this queue, which I showed as example. It's a great teaching example where you can get some basic stuff, how TLA Plus works, how to run it. And then I tried something a bit more complicated, and then I wrote this from scratch. So those two it's quite simple to start. It's not complicated. It looks a bit complicated, but once you get used to it, it's simple to use.
Okay, thank you, and thank you for your talk.
The way you said it seems like it was your decision to invest in TLA and do that. Did you ever manage to prove, for example, to management that this is a necessary step? Were you sponsored in this endeavor, or is it like only your good wish to do this?
I did it in my free time, so just at home I wrote it and validated it because I was afraid for this thing myself. But after I did it, management got interested. So at an internal presentation of this talk, they were asking if I can do presentation about just TLA+. Probably it will be a thing at Ubisoft, I don't know.
You said you caught a bug using TLA. I'm curious what kind of bug it found for you. What kind of bug would that look like?
The bug was about a deadlock when it could happen that the current scheduler worker goes to sleep and all the other workers also go to sleep, and still there are tasks in the front queue, which is nobody handling. This was a bug, and TLA Plus found this deadlock, and they just fixed it. So it can show you not only states, invalid states where your invariant is broken. TLA Plus can also detect deadlocks, so it can see when your system cannot progress anymore. So none of the actions is possible, and still the state is not considered final, and then it is a deadlock, and it will report how you can get into this deadlocked state from the initial one, again, following sequence of actions, and I just reproduced them, and indeed it was a deadlock.
Okay, so we are out of time. So please, a round of applause.